Welcome to this Concept Explainer brought to you by CBSE ScoreLab of ProfSam.com. Today we are starting a deep dive into Unit 3, Current Electricity. We'll be focusing specifically on a really critical and often misunderstood concept, the limitations of Ohm's law. We're going to make sure this topic is simple, clear, and that you really get the physics behind why this fundamental law sometimes fails. So we all know the equation V equals IR, right? It's pretty much the first thing we learn. But let me ask you a very simple everyday question. You take one of those old-style incandescent bulbs, with the coiled filament. Why does it often fuse or burn out right at the moment you switch it on and not, say, after it's been running for an hour?
Oh, that is so true. It always happens right at the start. I always thought maybe there's some kind of a current surge when you turn it on. But then our home voltage, the V, is constant, isn't it? So if V is constant and R is supposed to be constant, why would the current surge? I mean, it should just be V divided by R immediately.
Exactly. You have just articulated the core doubt every physics student has. And the simple reason is that for that bulb, the resistance R is not constant. Not at all. It changes drastically. The moment you flip that switch, the filament's material is already betraying that simple VIR relationship. So let's unpack this. The core idea is that Ohm's law describes a linear relationship. Super simple. You double the voltage, you double the current. It's a straight line proportionality. This is true for what we call ohmic materials, like a pure copper wire, as long as we keep the temperature steady.
Okay, so Ohm's law is more of a special case then, not some universal law for every single material out there.
Precisely. And materials that do not obey this simple linear rule are what we call non-ohmic materials. And here's a mental image to help with that. Imagine a hallway. The traffic moving through it is the current, I. And the pressure difference from one end to the other is the voltage, V. If the traffic flows perfectly linear with the pressure, that's Ohm's law, a constant, predictable hallway. Picture an adaptive hallway. This is our non-ohmic material. If the voltage pressure gets too high, maybe the walls of the hallway get hot and start to narrow the path.
So the resistance is increasing.
Yes. Or in other materials, maybe the high pressure actually opens up new side doors, letting a sudden flood of new traffic in.
So in this adaptive hallway, the structure itself, the resistance, is actually changing based on the voltage we apply. If the resistance changes, the VI relationship can't be a straight line anymore.
Absolutely right. That simple VIR rule is broken because R is not a constant. R is now a function of the conditions. So the VI graph for ohmic materials is that perfect straight line through the origin. But for non-ohmic materials, that VI graph is always a curve. It's nonlinear. And that curve tells us everything.
So understanding why the curve bends is the important part for the exam.
Exactly. It's the key. Now let's see how NSERT formally defines the perfect case, the one that does obey the law. Could you read out what the textbook says?
Okay, reading the definition now. It says, the electric current I flowing through a substance is proportional to the voltage V across its ends, i.e. V is proportional to I, or V equals Ri, where the proportionality constant R is the resistance of the conductor.
Excellent. The key phrase there is proportionality constant R. That's the part that fails in the real world. So let's break down the three main ways this proportionality fails. First, and the most common one, is that V is just not proportional to I. The VI graph becomes a curve. Our incandescent bulb filament is the perfect example. As current flows, the temperature skyrockets. It goes from room temperature to maybe 2,500 Kelvin. This incredible heat causes the atoms in the filament to vibrate much more violently.
Right. And I remember from the microscopic view of resistance, more vibrations mean more collisions for the electrons, so the relaxation time, tau, decreases, and since resistance is inversely proportional to tau, R goes up.
Correct. The VI ratio is continuously changing because R is changing with temperature. The VI curve bends upwards. That's the first limitation. The second limitation is when the VI relation depends on the sign of V. Think of a diode. If you apply a positive voltage, what we call forward bias, it conducts easily. Current flows. But if you reverse the polarity, apply a negative voltage, the diode almost completely blocks the current.
So it's like a one-way street for current, low resistance one way, and extremely high resistance the other way. The graph wouldn't be symmetric at all.
Exactly. The physics inside the p-n junction makes it directional. This is fundamentally different from just a simple temperature effect. And the third failure point, this one is a bit more advanced conceptually. It's high field effects. This happens in some semiconductors. If you apply a very, very strong electric field, so a high voltage over a tiny distance, the free electrons gain so much kinetic energy between collisions that when they finally do collide with an atom, they can actually knock out new electrons.
Wait a minute, knock out new electrons? You mean you're creating brand new charge carriers? That's called impact ionization, isn't it?
Yes, sometimes it even leads to something called avalanche breakdown. And this is the critical insight. The voltage is now so strong, it's actually changing the material itself by creating more carriers.
Right.
Now, think back to our resistivity formula. Rho equals m divided by ne squared tau.
Right. In the first case with the filament, only the collision time, tau, was changing because of heat. But here, with impact ionization, the number density in itself is increasing.
Precisely. That fundamental assumption that n is constant is now broken. This means the current can suddenly shoot up exponentially, much faster than the voltage that's causing it. It's an extremely nonlinear effect. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com too. Okay, let's make this concrete with the bulb example again. Let's put some numbers to it. Let's say we have a standard tungsten filament. When it's running hot at 2500 Kelvin, its steady-state resistance, let's call it R hot, is about 240 ohms.
Okay, 240 ohms when it's glowing.
Right. But if we measure its resistance when it's cold, at room temperature, R cold is drastically lower. It's only about 24.5 ohms.
Wow, that's almost a 10 times difference. I had no idea it was that huge.
It is. Now let's say our supply voltage is 120 volts. The normal steady current is I hot, which is 120 volts divided by 240 ohms.
Right.
That gives us 0.5 amps. That's its safe operating current. But the moment you flip the switch, the filament is cold, right?
Yes, its resistance is only 24.5 ohms.
So the initial inrush current, I cold, is 120 volts divided by 24.5 ohms. That comes out to roughly 4.9 amps.
12.9 amps. Compared to the normal 0.5 amps, no wonder the filament gets stressed and eventually breaks.
That's the one. It's pure non-ohmic behavior in action. Now, this non-ohmic behavior isn't some flaw. It's actually the key that unlocks almost all of modern electronics. Understanding when Ohm's law breaks is what allows us to study and build semiconductor devices, diodes, LEDs, transistors. They all rely on this nonlinearity to work. Okay, moving on. Let's talk about 3 common conceptual traps, the silent killers that can make you lose marks. Misconception number 1. Students assume Ohm's law is universal. So if they get a curved VI graph in the lab, they think their experiment is wrong. The correct idea is that Ohm's law only applies to ohmic materials under steady conditions. Devices like diodes are designed to be non-ohmic. You are supposed to see a curve.
So I shouldn't think the curve is an error. I should think, this device is non-ohmic. Okay, what's the second one?
Misconception number 2. Students simplify a diode in their head. They think it's just a resistor with very high R in one direction and very low R in the other. The correct idea is that it's much more complex. A diode's relationship is exponential. It's not just high or low R. It's governed by complex junction physics, totally different from a simple resistor. And the third one, this is a bit more analytical. Students think that even for a non-ohmic device, you can just pick a point on the curve and calculate its resistance using R equals a VI.
But you can calculate that ratio? No.
You can, but that value, which we call static resistance, is almost meaningless for predicting what will happen next.
Why is that? If I calculate R equals VI at some point.
Because that's the slope of the line from the origin to that point. It doesn't tell you about the shape of the curve at that point. For any real analysis, we need the slope of the tangent to the curve at that point. We call this the differential resistance, and its formula is R dVdI.
I see. So R dVdI tells you how the current will change for a small change in voltage right at that specific operating point.
Precisely. For your exams, when you analyze non-ohmic devices, you have to think in terms of differential resistance. R equals dVdI, not the simple VI ratio.
Okay, got it. So for a diode, I must remember its resistance R depends completely on the voltage I'm applying, and I need to think about the slope, dVdI.
Absolutely. Now you're thinking like an engineer.
Yep.
Okay, well, let's lock this in with some memory anchors to make sure it sticks. For linear devices, remember the simple rule, R, V of I, constant resistance. For nonlinear devices, remember the calculus rule, R equals dVdI, varying differential resistance. And a simple phrase to remember, Ohm's law fails when the resistance isn't constant. And here's a physical gesture. Hold a pen or pencil straight up.
Okay.
This straight line is your ohmic material's VI graph. The slope, the resistance, is constant. Now, gently bend the pencil or just curve your finger. That's your non-ohmic material. The curve tells you the slope, the resistance, is changing continuously. The more it bends, the more non-ohmic it is. All right, let's quickly summarize the key factual takeaways for your exam. 1. Ohm's law, VIR, only applies to ohmic materials where R is constant. Non-ohmic devices like diodes or hot filaments have non-linear VI graphs. 2. Non-ohmicity happens mainly for 2 reasons. Either the temperature changes the collision time, like in a filament, or a high voltage changes the carrier density N, like with impact ionization. And 3. To analyze non-ohmic devices, you must use their VI curves and the concept of differential resistance, which is R equals dV/dI, the slope of the curve. Remember, to get maximum marks in 12th CBSE Physics, Chemistry, and Math, visit ProfSam.com.
That is ProfSam.com, right?
Yes, all the very best for your preparation. Keep learning and keep diving deep into the fundamentals.